Good afternoon. We're going to start with the session A, pattern recognition and machine learning techniques. And the first presentation is a statistical evaluation of Sesamo encoder for pattern recognition and categorical data by Eric Valdez Valenzuela.
Thanks. Hi everyone, my name is Eric Valdez and I'm going to present a work titled Statistical Evaluation of Sesamo encoder for Pattern Preservation in Categorical Data. And this is the agenda for this presentation. I'm going to start by highlighting the relevance of categorical attributes in supervised machine learning algorithms. Then I will introduce some related studies. Then I move on with the goal of this work, our methodology, or experimental results, and I will finalize with our conclusions and our takeaways. So categorical attributes are variables that represents discrete and non-numerical instances within a data set, right? And these kind of attributes classify data into distinct groups based on qualitative properties of the data, right? For example, here we have the categorical attribute level of education, which may classify a person into one of the next group: high school, bachelor degree, master degree, PhD, and so forth. So most of the data sets used to train machine learning models contain this kind of attributes, right? And on the other hand, most of the machine learning models exclusively work with numerical attributes, right? Like the logistic regression, a neural network, and a super vector machine. So if we want to take advantage of the existing information in this kind of attributes, we have to apply a spatial processing to these kind of attributes. So why it's important to properly handle categorical attributes? As I mentioned before, real-world data sets typically contain a mix of both categorical attributes and numerical variables, right? And we cannot just omit or delete these kind of attributes because they may provide relevant information to the machine learning algorithms. So to effectively employ these categorical variables in machine learning models, we have to process them through an encoding method, which essentially means that we have to convert the categorical instances into a number, right? To map a categorical value into a number. And here it is crucial that this mapping retains the underlying pattern in the data, right? Because otherwise there could be a loss of information that could negatively affect the performance of some machine learning algorithms. Okay, so how can we quantify the impact of categorical encoders in machine learning algorithms? First of all, here I want to highlight that measuring the effectiveness of encoders is a very important task because this allows us to quantify how well an encoder preserves the underlying pattern, right? And this also helps us to measure how this pattern retention affects the performance of machine learning models, right? And as we will see later, each encoder technique has a different effect on the different machine learning models, right? And there are several studies or benchmarks that have measured how the different categorical encoders affects the different machine learning models, right? And what these studies typically do is to subjectively select a fixed number of data sets, then take multiple encoders, and then evaluate the performance of these encoders with different machine learning models, right? And as you can see, some machine learning models may have a different performance based on the encoder that we use, right? So here we have some related works, and as you can see, actually, this is the state of the art. Some of these works were done like 2 or 3 months ago, right? And here we have the author, the total data set used, the total encoders, the machine learning algorithms used, and a brief conclusion. And for example, Matucci used 50 data sets with 32 encoders with 5 machine learning models, and they found out that the weight of evidence performed best for decision trees, right? And actually, like 3 years ago, we conducted a study where we used 7 data sets, 10 encoders, 5 machine learning models, and we found out that neural networks and supervector machine were little affected either negatively or positively for the different encoders, right? And so forth. We have different studies. And the advantage of these studies is that they offer strong evidence that some encoders perform better than others, right? Which means that it's important to properly select the encoder that you want to use based also on the model that you will use to solve your problem. But on the other hand, a large disadvantage of all these studies is that they lack a statistical support or statistical rigor, in the sense that why choose only 50 data sets and not 100 or 1,000 or 10,000 data sets? So maybe a better question is, how many data sets are enough to say that my conclusions are solid enough or that are supported by a statistical criterion, right? So, it's not working. Okay. So the goal of this work is based on the disadvantages of the previous works. Our main goal was to conduct a quantifiable statistical evaluation of the encoders, right? And that means that instead of arbitrarily selecting a fixed number of data sets, we evaluated the encoder on as many data sets as required until we reach an statistical significance or an statistical criterion, right? And something very important here is that we don't know a priori how many data sets will be required until we reach this statistical criterion. So to solve that problem, we use synthetic data sets. And moreover, the assessment of this study included the Sesamo encoder, which is a novel type of encoding that captures the relationship between the categorical attributes and the other attributes, what we call pattern-perceiving codes. Okay, so this is the methodology that we followed. As you can see, we first define the performance metric, and something important here is that this metric has to be also supported by an statistical criterion. Then we generated the synthetic data sets. Then we moved on to the statistical evaluation of the encoders, and finally we analyzed our results. Okay, so let's move on to the first step in our methodology. So to measure the performance of the encoders, we use the minimum error, right? And the rationale behind this error is that any encoder is associated with an error distribution, right? Which represents the population of all the potential errors that may arise when someone uses this technique, right? And as we know, this error distribution is characterized by its mean and by its standard deviation, right? And the minimum error is a value position at k standard deviations to the left of the mean within the error distribution, right? And this metric is based on the Chebyshev inequality, which in summary states that for any population, you can say that at least certain portion of the data can be found at k standard deviation from the mean. And something important is that this applied regardless of the shape of the distribution, right? So in summary, what we are looking here is we want to find this error, right? The error located at root square 5 standard deviation to the left of the mean. Okay, then as I mentioned before, determining the error distribution of an encoding involves evaluating it with many data sets until we reach an statistical criterion, right? And the challenge here is that we lack prior knowledge about the exact number of data sets that we will need, right? And to tackle this challenge, we employ synthetic data sets, which were generated through a polynomial functions. And also something very important here is that to emulate the properties that you can find in real-world data sets, we analyze real-world data sets, and based on that, we define some ranges that are input into the framework that generate the synthetic data sets in such a way that we guarantee that each synthetic data set is different from the previous one, right? And actually, this synthetic data generation is available and is open in GitHub. Okay, so let's move on to the evaluated encoders. These were the encoders that we evaluate. We have the ordinal encoder, the one hot, the binary, the count, the hashing, and the sesame encoder. And on the other hand, there we have the supervised machine learning algorithms. We have a neural network, a logistic regression, a supervector machine, a Gaussian I-base, and the XGBoost, right? And all the encoders and supervised machine learning algorithms were combined to ensure that all models was tested with all the encoders. And we finally have 30 combination of models and encoders. Okay, so let's move on to the evaluation of encoders. And before applying the evaluation, something important was that we convert the synthetic data sets into a balanced classification problem, which means that in the target we had 50 positive instances and 50% of negative instances, right? And the next step was to determine the statistical criterion to stop evaluating the encoders, which was until the mean distribution of the error reaches normality, right? That was the statistical criterion to stop sampling different synthetic data sets, okay? So once we define that, we move on to the evaluation. And these were the steps that we followed. First, we create a synthetic data set using the polynomial function. Then we apply the encoding techniques and replace the categorical instances in the data set. Then we solve the encoded data sets with a machine learning algorithm, and we record the resulting error. Then we repeat the steps 1, 2, and 3 until we reach 36 errors. And then we compute and record the mean of the errors, right? And once we have at least 36 errors, we verify if the errors mean distribution is normal or is Gaussian. If this is true, we proceed to step 7. Otherwise, we have to repeat all the previous steps. And finally, if we reach normality, we conclude the sampling process and determine the mean and the standard deviation from the errors mean distribution, right? And actually, this benchmark is also available and open in GitHub. I know that there is a lot of information here, but something that is important to clarify is number 7, right? How did we determine that the errors mean distribution is normal? And to do so, we use the L distribution. This distribution is very similar to the chi-square, but the difference with this distribution is that this guarantees that the distribution is normal or Gaussian, right? Well, so let's move on to the results. We evaluated encoders with roughly 3,000 data sets until we reached the statistical criterion, which was achieve normality. Once we knew the mean of the error distribution, we determined its standard deviation and the mean. And here are the results that we got. So as you can see, Sesame was the encoder that got the lowest mean error, the lowest mean error. And here, since we are speaking about error, the lower the error, the better the performance, right? And also something important is that our findings are aligned with the analyzed related works, right? Which this is good. Which, for example, Xu also found that the one-hot encoding performs better for neural networks. Matucci found that the one-hot encoder achieved superior performance with the logistic regression. And finally, Pargent also observed a poor performance with the ordinal encoder and with the count encoder. Okay, so let's move on to our takeaways. And our main contribution in this work is that we evaluated encoders with a statistical criterion, right? And we also employ the minimum error metric, which represents the values evaded at high standard deviations from the left of the mean of the error distribution. And also, to evaluate the encoders, we use synthetic data sets. The encoders were combined with 5 machine learning models, and on average, each model encoder combination took approximately 3,000 data sets until they reached the error mean normality. Sesamo achieved the lowest minimum error, which indicate that it had the best performance, followed by the ordinal encoder. On the other hand, the ordinal encoder, which is a widely used technique, showed the poorest performance among all the encoders. And finally, our findings are aligned with the existing benchmark, which that's good. And that's all. Thank you.
Thank you for your presentation, Eric. Now it's time for question. Anyone has questions?
Thank you for your presentation. Your conclusions, you remarked that Sesamo is the technique that reached the lowest error.
That's right.
Could you elaborate a little bit more why?
Yeah, actually, the Sesamo encoders deserves its own presentation because it's a large topic, but in summary, what the techniques does is very different to the conventional techniques because these techniques samples a lot of candidate codes, which means takes random numbers and then evaluate this number into an approximation function, which is a polynomial, and then we sample a lot of numbers, a lot of codes randomly. And once we reach an statistical criterion also, until the error distribution of the mean of the error becomes normal, we stop the process and we get those codes. We got the lowest error when we sample, when we evaluate them in the approximation function. So in summary, Sesamo got the best performance because these techniques seeks for the pattern preserving codes, right? Yeah. Well, as its name says, that are those codes that preserve the underlying pattern in a data set, right? As we know, there is an unknown function that relates one categorical attributes with the other attributes, right? We don't know the form of this function, it's unknown. But what we can do is use an approximation function to try to find out that function, which obtain the minimum error with the pattern preserving codes.
Okay, thank you.
Thank you. Any other questions? No.
Could you tell us, please, why do you have to use a special distribution to determine whether the samples that you're getting are normally distributed?
Yeah, that's also a large topic, and it also deserves its own presentation, but in summary is that the commonly used tests to try to identify a normal distribution or a Gaussian distribution are based on rejecting or accepting your null hypothesis, right? Which in this case is to know if your distribution is normal, right? The problem with this conventional test, like the chi-square and the Shapiro wheel, is that what they do is, if they reject the hypothesis, they say, okay, I didn't find enough evidence to say that your distribution is Gaussian. Do whatever you want with that information, but I cannot guarantee that that distribution is Gaussian. I just didn't find enough evidence to reject your null hypothesis. On the other hand, the L distribution, it guarantees that your distribution is Gaussian, because this is based on, when this distribution was done, it was tested through a Monte Carlo simulation where the authors took a lot of Gaussian distribution and then evaluated through the chi-square, the original chi-square test, and they found out some specific values in such a way that if you use the L distribution and you get those values that are predefined, then you can guarantee with certain probability that your distribution is Gaussian. Yes, that's a summary.
you choose 36 errors?
Yeah, that's also a very common question, and this is a rule of thumb based on an ancient rule that the people that do statistics uses. I mean, there is not a mathematical proof that can tell you why 36, but it's just a rule of thumb.
And in the last of your conclusion, if the ordinal is, well, is what exceeds the previous performance,
Yeah.
why is used, or why is still using?
Yeah, that's also a very good question. And there is a rationale behind, and is that this technique, the ordinal encoder, may introduce an unexisting order in data that originally it doesn't have. It doesn't have an order, right? Because there are two types of categorical attributes, the nominal one and the ordinal one, right? The ordinal, it has a natural order, and the nominal, it doesn't, right? The color of the eyes from the people, red, green, or whatever. This kind of attribute, it doesn't have a natural order, right? And if you use the ordinal encoder with this kind of attributes, you are introducing a non-existing pattern, right? And that makes that the machine learning models make up, or I don't know, it introduces non-existing pattern. That's the answer. Thanks.
Any other question? So, thank you, Eric. This is your. Okay, the next presentation is Diversity in Genetic Algorithms in the Generation of School Schedules by Alejandro Moreno Martinez.
Hi. Hello, everyone. Good afternoon. My name is Alejandro Moreno from the UAM Valle de México. I'm going to present my master research with the title Diversity in Genetic Algorithms in Generation of School Schedules. On this presentation, I give you an introduction talking about the genetic algorithms in the interval generation, diversity in the population, metrics for measuring the diversity, and I comment about the dataset use and experimental setup, some resource, and conclude with the conclusion and some reference. Okay, let's start with the introduction. Generate a school timetable is a complex task. For that reason, use genetic algorithms can provide promising solutions, but it's essential the diversity in these algorithms because the diversity in the algorithms with the population to ensure exploring across the search space, thereby avoiding falling into local optimas. That is a diversity metric measures the degree of difference between two individuals. Okay, the genetic algorithms, that algorithms are based in individuals. That individuals is composed by groups, and that's groups formed by teachers, classroom, venues or classrooms, periods. That's individual and evolve across to the generation to improve a better solution. In the case of timetable, the genetic can provide can find an effective solution. Well, the diversity in the population, when reference the genetic variation present in the individuals, Uh, for that, it's important to maintain the diversity across the generation to avoid a converging prematurely local optimal. Thus, it's important to explore more options for you can obtain the better solution. So, for that reason, it's important realize that study of to do this work, and in this present I showed some metric for measure the diversity and to evaluate different individuals. The first metric used is a Hamming distance. This metric calculates two individuals and select the difference between the same group, where compared this process was repeated in all individuals. For example, in this timetable, we have three differences in the in this case the teachers, and 1 day in the subject of programming is different. In this case, it's Wednesday, and that is Friday. But for use that metric, I need to normalize. For that, I divide the number of difference for the total elements existing in the individuals. But if you only do that, normalize, obtain the different normalize. For that, convert negative and plus one, and that gives the result on the in similitude existing individuals. The second metric is a Hamming distance. That's metric comparing two individuals by examining the number of shaders, elements between the relative and total number of elements. This is the equation for calculate that that metric. Take the set of the absolute value in the set A intersection B divides absolute value the set B union B. And taking the previous example, only we have two registers similar in the two tables, and that metric return the number of the 0 and 1, or is return the number that normalized. And finally, metrics used is the Euclidean and Manhattan distance. Euclidean distance between the 2 points to calculate as the length on the shortest lane connecting both points, and Manhattan calculate by adding absolute difference of the coordinates 2 points. It takes the difference in horizontal position and adds a difference in vertical position. For use that metric, I need do two things. The first, I need to transform my type of data, because I work with phenotypes. If you work phenotypes and don't have working that's metric, but that's in the case of Manhattan and Euclidean, only work with a type of numeric. For that, I convert my phenotypes and numerics, and use the equation for calculating n-dimensional, for compared groups in the same individual. And well, the dataset used for this work is the OR library, in specific the HTTT4. That is a dataset simply. That is a representation of the set. In this case, only have 4 venues, and we have a teacher, subjects, and that is the periods. For example, the venue 1, the teacher 1 give the subject 1 in two times. I and the reason for use is for that simply and use for testing the algorithm. So, no. My experiment are set to use that's parameters used for the genetic algorithm in following for 10 independent runs. I use a 10,000 generation to 100 individuals. Use a tournament selection and later testing with random selection. In both cases, I only take it the 75% of the original population, and that's individuals. We have the chance for create the offsprings, and uniform crossover approach with a 70% probability the interchange your information, and mutation applied with 20% of probability of modify some GNU value in the individual. And finally, I use an operative of elite teams. In this case, only taking the 10% of the best individuals existing in the population. Well, that is my resource. In this case, on the top show the Jacquard and Hamming distance, while below is the Euclidean and Manhattan distance. No, you can appreciate we have a low diversity in this population. That's resources after to the 10,000 generations. And for that reason, I decided use another type of selection for see what happened, or maybe that's better the diversity. And in this case, use operation the random selection, and yes, better the diversity. You can compare the resource. No, we have more diversity exists in the population, and in both cases, you can appreciate the Jacquard and Jacquard are similar, present same resource, but in case the Euclidean and Manhattan present high values of diversity. In some cases, you can appreciate some individuals. For example, in this area, you can appreciate some individuals is sequence, and I will explain exactly what present. This is a symmetric triangle. It's the same individuals to 0 100 individual, and it's the same that triangle with the on the top. Only namas, only saying that, and this 10 first individuals is the elliptis. We take it. And on this table, I compared the time of execution. In different selection. In both type of selection, the Hamming distance is better. But in tournament selection is faster compared with random selection. But you can, if you is a tournament, you lose more diversity compared with the random selection. And well, my conclusion is the first point, assessing population diversity, use individual similarities, provides value signals into genetic algorithms, behavior and in error correction, select appropriate metrics to specific problem is crucial. For instance, Manhattan and Euclidean distance metric may not always be applied or useful even with modification. Conducting various tests is A/B size to determine optimal parameters value for the specific problem. No, and the type of selection significantly influences population diversity. Tournament selection, effective for the scheduler problems, then to favor of the best individual, potentially leading to homogeneous overgeneration. In the case of random selection, maintains diversity by according individuals with biting adaptable levers. The future works involves exploratory techniques to evaluate the flexibility and performance of each metric and testing different operators to assess the impact on the population diversity. That is some reference use, and that is all. Thank you for your attention.
Thank you for your presentation, Alejandro. Any questions?
What do you think it would happen if you increase the size of the population in, to the diversity of the,
Sorry, what? Can you repeat the question, please?
what do you think it will happen if you increase the size of the population with the diversity? You have 100, and if you increase the size, it will increase or decrease the diversity.
Maybe you can repeat in Spanish, please. I really understand the final question.
¿Qué crees que pasaría si incrementas el tamaño de la población? Porque ahorita tienes 100.
Ah.
O sea, si incrementas a 300, a 500, con tus métricas, ¿debería de bajar o debería de, crees que incremente o que se mantenga la diversidad? No lo sé.
Well, I try to respond in English, no, but I really don't have idea. Maybe no, the diversity, no, the value of diversity height, no, no, I don't know really. I don't checking that. I don't sure what answer that.
Thank you, Alejandro. Any other question?
Thank you for the presentation. You are considering diversity in the search space because you are using distances to determine how close are individuals. But what happens if you have two individuals which are very close with a minimum distance, but the fitness value is very different? You have one which is a bad one, and you have another one close to that bad one, which is a very good solution. So how important is to maintain such a diversity if the benefit in the fitness function is not reflected in that diversity measure?
In this case, is for if you only have a small space searching, you don't can make more options for evaluate. Sorry if my English is not good.
Maybe you can answer in Spanish if you want.
Ok. Gracias. Bueno, la diversidad nos puede ayudar bastante en el aspecto de que al tener múltiples cantidades de podemos hacer esas cantidades de combinaciones y encontrar una mejor solución. En este trabajo aquí no lo estoy haciendo, sino es en mi tesis, donde estoy implementando otro tipo de funciones como inicialización y reparación. En este caso, las de reparación sí llegan a como hacer una gran variación entre los individuos y sí permite que pueda converger el horario.
Sí, aquí el punto es, tú estás vigilando dices que si hay mucha diversidad el algoritmo puede encontrar mejores soluciones. Pero eso es al principio, no más adelante. Más adelante quieres que converjan. ¿Y qué pasa si al converger tu diversidad te dice que tiene soluciones que, digamos, ya son muy parecidas, ya la diversidad es muy baja, pero realmente en aptitud son muy diferentes? O sea, el punto es que cuando tú manejas diversidad en un algoritmo evolutivo, está bien ver qué tan dispersas están las soluciones, pero también tienes que considerar el paisaje de las aptitudes para poder determinar realmente qué tanto está influenciando qué tan separadas o juntas están las soluciones en el espacio de búsqueda, pero también qué tan buenas o malas son, dependiendo de qué tan cerca o lejos están. Ese es mi punto. O sea, no puedes, bueno, lo puedes hacer, pero creo que te daría mayor riqueza si también estás considerando diversidad, considerando la función objetiva.
Ok.
¿Sale?
Sí, la verdad ahorita no lo había considerado como el punto que usted lo menciona.
Muy bien.
Lo voy a tomar en cuenta.
Gracias.
I have two questions. The first one is, do you have a strategy to start the initial population in order to see if are distributed the initial solutions for your problem along the search space?
Sorry, what? Sorry, I don't can very good.
Si tienes alguna estrategia en específico para iniciar tu población al momento de generar tus soluciones, o se hace de manera aleatoria para verificar que sí exista pues diversidad dentro de tu población inicial, porque al menos observo que en tus parámetros solamente tienes 100 individuos.
Bueno, en este caso sí son iniciados completamente aleatoriamente. O sea, no se quedan a partir, sí, aleatorio.
Y la segunda pregunta es, ¿en qué generaciones estás evaluando la diversidad? ¿La evalúas al final, al inicio, en medio?
Las evalúo hasta el final.
Sí, ahí yo creo que sería interesante monitorear la diversidad durante el proceso evolutivo, porque estás verificando al final y agregando o retomando lo que decía el doctor Fren, es que al final es obvio que el algoritmo converge, las soluciones son muy parecidas, y es a lo que tiende un algoritmo evolutivo, que converja, y pues está llegando a la buena solución. Al inicio debe haber más diversidad. Creo, en mi punto de vista, sería interesante ver cómo la diversidad va decreciendo de acuerdo al proceso evolutivo, y en qué momento empieza a pues, a parecerse más las soluciones. Sería un buen experimento para que se incluya en tu investigación, porque al final obviamente pues, por naturaleza las soluciones son muy parecidas, están muy cerca, pero si se empieza a evaluar desde antes sería en mi punto de vista sería más beneficioso estar monitoreando la diversidad, porque pues está cubriendo un espacio de búsqueda más amplio. Gracias.
Thank you. Any other questions? Okay, thank you for your presentation, Alejandro. This is your diploma. Okay, the next presentation is multi-objective assignment of citizens to INE service modules using NSGI2 and efficient optimization approach by Edgar Jardon. Okay, we are going to move on to the next presentation, that is Feature Engineering for Music Speech Detection in Costa Rica Radio Broadcast by Juan Ángel Acosta Ceja.
Okay. Hello, good afternoon. My name is Juan Ángel Acosta Ceja. I am a master student at the Huanco Xalapa in Mexico City. I am a mathematician. Sorry for my bad English. My English is not good, but I wanted to present my work in this conference. Okay, I am going to talk about the very simple idea for a future selection. Okay, my title of my presentation is the future engineering for music speech detection in Costa Rica radio broadcast. This is my content of my presentation. I will start introduction the problem statement and objectives. Then I will talk about the selection methods, in this case individuals and the party-wise future selection. Then I will describe my methodology and the steps of my experimentations. Then I will the analysis result and discussion. I will define the Pareto front and evaluation. And the end, I will discuss the conclusion and the future work. Then to start, one of the problem in artificial intelligence or machine learning is the high dimensionality or dimensionality reduction. This problem is important because we are looking the best filter for any problems, for classification or for prediction. Okay, this problem helps to reduce the execution times. In some case, the performance of the algorithms. Okay, in recent years, we have a significant increase in multimedia data. For example, for video images, audio from radio and television broadcasts, and podcasts. Due to this, it's impossible to create the labels, description, and transcription manually. Okay, for these reasons, one of the problems in audio content analysis, the ACA, is the classification of the speech and the music. It's very easy. For this reason, to resolve this problem, the Dr. Marvin Cotto at Universidad de Costa Rica, they created a data set that has 178 music files and 778 clean voices. That it's important to say that they used 136 filters, okay, that are divided in three sets: the energy sets, MNC sets, and the chroma. These three sets, filter sets, it's too similar because they're using the mean, the HTD, the delta filters, among others. Okay, okay. On the other hand, they used 4 typical classification algorithms: the naive Bayes, the random forest, KNN, and SUVM. This is the two best two classification algorithms. For KNN, the best performance is the energy with MCC, MCC with chroma, and all data with a 0.981 in precision. For SUVM, the best performance is the energy with MCC, energy with chroma, and all data. Okay, for that with precision, the 0.94. Okay, it's important to say that they reduce the filter sets for each algorithm. Okay, for this reason, in this work, we have 2 main objectives. The first, we want to select the best filter for classification algorithms, in this case, SUVM and the KN. And the second, we want to choose the best classification algorithm for the new filter sets, okay? In general, we are looking, it's an order in the importance of the filter sets, okay? For these reasons, we have a 2 filter selection, the individuals and the pairwise filter selection. For individuals, we have a low variance method. In general, we are interested in filters that have a low variance because these filters has the same value in all samples in general. But these filters will not interesting in our problem. Okay, for case a lasso, the importance of the filter is the coefficient obtained on lasso. Okay, for example, if a filter has a 0 coefficient, this filter will be eliminated in our problem. For the decision tree, the most important filters are at the top level in the tree, while the less important filters are the bottom level. Okay, in general, but we're interested in the 2 algorithms, the CAR and ED3. for in our problem. Then we have other dispersion methods. For example, the mean absolute difference that is similar to low variance because we are interested in the filters that have a more dispersion data. Okay, in general, filters with a higher math have a more dispersion data. The only difference is the square. Okay, in this case is the absolute. But wait, we have two examples. The first has a low math, and the second has the higher math. Other dispersion method is the dispersion ratio. This method is defined as division between the mean and the geometric mean. It's the same for math. We have a low DR and the higher DR. Okay. For case and pairwise filter selection, we have two old friends. Okay, and the chi-square test and the Pearson correlation. In this case, for chi-square test, we interested the filters. We want a great dependence between the target variables and other variables. In general, a larger chi-square value commonly indicates a higher dependence between the two variables. For case of the Pearson correlations, it's too similar because we interested the filters that have a more correlation with a target variable. In other words, that are interested the filters that have that close to 1 in absolute value. Okay, and okay. In our methodology, has two steps. The first is to find the best filters. Is to find the best filters for each selection methods. Then, in this case, the maximum number of the filters in our problem is the 60% filters because after this percent, the performance in all methods has the more performance in that all methods. Okay, and the second steps, we created the 10 different training and the test sets using the 30% of the data testing. Finally, we get the Avenger for the performance graph. For create this performance graph, I'm using the voting, the approval voting. This is the new filter selection, because we select the filters that have a minimal votes. In this case, 8, 7, 6, and 5 votes. Okay. Then we train the methods. In this case, the KNN and SUVM. The next, it's difficult to compare two methods. It's difficult because we have two aspects. The first is the number of the filters, and the second is the performance. In this case, Pareto front has an order partial. For example, we have methods to compare two methods. One method is better than other methods if has less filters and the higher accuracy or performance. Okay. For example, we have a table of evaluation for KNN for each method. In this case, the best method is the ED3 and the approval voting 8. Okay. This method is the best because ED3 is the best it's the best method because has the less number of the filters and the more accuracy, or in this case accuracy. Approval voting is the same. For case SUVM, the best performance is the approval voting 5, and approval voting 7, and approval voting 8. It's the same case. This is the best best methods in this area. This is the best methods in this area, and this approval button is the best methods in this area. Okay, to compare it to these tables, we have the best is the approval button 5 and approval button 7 for SUVM and approval button 8 for KNN. This is the best performance in all problem. Okay, the best filters in this case is the initial MLCC and the letter chromas, and the other filters that are not in this table because it's very big, the table. And the worst filter selection, the PCA and DR, are the best selecting the worst filters. Okay, and okay. For conclusion, combined filters from the MLCC, chroma, and energy sets for the best results. Approval button inducing general description of the characteristics. In other words, these filters are the good in many aspects. For example, if I want to filters that have a more dispersion data, reduce the entropy, maximize the information gain, and greater correlation. Okay, with a objective variable. With good selection, classification methods can significantly improve performance in classification algorithms with the less performance. Then, it's possible to reduce the number of filters with the same performance. It's important. Once the problem algorithm is better than other algorithms depending on the set of the filters. Then, for a future work, filter investigation should delve into the types analysis of the MLCC and the chroma filters, because we believe there are possible bias-specific music, gender, or male on the female voices. Create the synthetic data to observe model execution times, investigate the new filter selection techniques, give different ways to the vote for each method for approval voting. Okay, this is my reference, and thank you for your time.
Thank you for your presentation, Juan Angel. Any questions?
Please, my English is not good, but his preference is if you talk in Spanish, please.
So my question is, no, solo no me quedó muy claro lo de PCA. ¿Qué fue lo que pasó con PCA en los resultados?
Es que PCA, para hacer la selección de características en PCA hay un pequeño problema con la parte de la selección de los centroides. En este caso, como se utilizan arbitrariamente, bueno, en este trabajo al menos no tuvimos pues, sí, tanto cuidado, o no tuvimos como la paciencia para revisar ese tipo de casos de los centroides. Entonces creemos que justamente al seleccionar los centroides lo hicimos mal. Por eso, a pesar de que tuvo buenos resultados, bueno, porque sí tuvo buenos resultados, escoger malos filters no significa que sea malo el performance, por ejemplo, en general, pero sigue teniendo una gran cantidad de filters malos con una cantidad de performance menor a los demás, ¿no? En el caso de DR, pues ahí creemos que como se utiliza la media geométrica, al calcular la media geométrica, pues es una raíz enésima en general. Entonces, para calcular ese, sentimos que hay un pequeño sesgo, un pequeño error al calcular ese tipo al ordenar la importancia de los filters, ¿no?
Okay.
¿Sí?
Gracias. Felicidades.
Gracias.
Ok, gracias por tu presentación. Entonces, PCA es un método no supervisado.
Ajá.
¿Usaste algún método supervisado, no sé, como LDA o CDA?
No, bueno, este es un pequeño trabajo que yo hice en una estancia de investigación allá en Costa Rica. En general, bueno, yo estoy haciendo mi proyecto de tesis de maestría, pero utilizando no técnicas tanto de machine learning, sino introduciendo otros aspectos, pero más matemáticos, ¿no? O sea, en el sentido matemático con otras áreas de, por ejemplo, teoría de gráficas, ¿no? Que no se ha explorado mucho sobre esa área, e intentamos introducir ese tipo de áreas nuevas, entre comillas, justamente a la parte de la selección de características, y hasta ahorita pues está funcionando bastante bien, me estoy emocionando, pero sí, hay que investigar mucho más de otras técnicas, al menos en inteligencia artificial, sí hay que investigar muchas más técnicas.
Ok, gracias.
Sí.
¿Alguien más tiene alguna pregunta? Muy bien, gracias. Muchas gracias. Okay, this was the last presentation of this session. So I remember you that we will have the keynote at 5 o'clock. So see you later. Thank you.